All right, this video will focus on what is called the limit of a function. So we have the function f of x equals x squared minus 2x plus 3. I think we can all agree that because it's a second degree polynomial, it would be or make a parabola. What you see here are 3 screenshots from one of your TI-84 graphing calculators. So this is the function that we put in, y equals x squared minus 2x plus 3. This is the table screen, all right? So when x is 0, y is 3. When x is 1, y is 2. When x is 2, y is 3, and so on. And you could get those y values by simply plugging these x values in. So if I plug a 0 in for x, 0 squared minus 2 times 0 plus 3, that would work out to be a 3. Okay? And if you hit the graph button, this is what the screen would show. Now keep in mind that the window, we're only looking at positive x values, so from 0 to 3, 4, 5, 6, and from 0 to 1, 2, 4, 5, 6, 7, 8, 9, 10 on the y scale. All right, but that's what you would see. That's the portion of the parabola you would see. Now, it says we can see that f at 2 equals 3. Well, where can you see that? Okay, you can see it here in the table, or you can see it here on the graph. Okay, there's nothing really earth-shattering about that. It's pretty straightforward. Okay, so if you're given an equation, you can just plug the x value in. 2 squared is 4, minus 2 times 2, that's 4. So 4 minus 4 would give you 0, plus 3 would give you 3. Or if you're looking at a graph, you could go to where x equals 2 and go up until you hit the curve, or maybe you have to go down. In this case, I have to go up 1, 2, 3 units. Now, it wants us to examine the behavior closer, or as we get closer and closer to x equals 2. So look what's happening to the y values as I move towards 2 from the left-hand side. So from numbers that are smaller than 2. So I go from 1.85 to 1.9 to 1.95. Look at the y values. They're going from 2.7 to 2.8 to 2.9. If I come from the right side, if I come from 2.15, then down to 2.1, then down to 2.05, remember I'm moving closer and closer to an x value of 2. Look what's happening to the y values, 3.3, 3.2, 3.1. Until I get to an x value of 2, the y value is 3. So this is what this little table shows us. As x gets closer to 2 from the left, y is getting closer to 3. And as x gets closer to 2 from the right, so from these numbers right of 2, I'm coming towards 2, y is getting closer to 3 as well. So from that, we arrive at this notion of something called a limit. And a limit says, as x approaches 2, f of x, or as x approaches a, any x value at all, f of x approaches L. So this is kind of the notation of a limit. We write the limit as x approaches a, and that's how you read that, the limit as x approaches a of f of x of your function equals L. And in this case, as x approaches 2, so I'm approaching an x value of 2, so I would replace the a with a 2, my f of x would approach a height of 3. You may also see this written as the limit as x approaches 2 of f of x, remember, was x squared minus 2x plus 3. Okay, that's coming from up here, x squared minus 2x plus 3. That is the equation of f of x. That is equal to 3. And that's how we read it. The limit of the function f of x as x approaches 2 is equal to 3. So this is what limit notation looks like. Now, there's a couple ways to solve a limit. If you're given the graph, okay, you could just read it from the graph as x approaches 2, so I go to where x equals 2, and again, I'd have to go up until I hit the curve, and I hit the curve at a height of 3. You're looking for the function's intended height. The other option is to try direct substitution. So if I don't see this graph here, without the picture, I'll just block it out. I could try to substitute a 2 in for x. 2 squared is 4. 2 times 2 is 4. That would say 4 minus 4, 0, plus 3. I'd get 3. Either way, I'm going to get 3. Okay? Now, common sense definition of a limit. A limit is the function's intended height. And that might not make a whole lot of sense right now because we've really only looked at something called, up to this point, continuous functions. I guess that's not true. We did look at some piecewise functions, but for the most part, our functions were continuous. All right, they looked something like this, or like this, all right, or maybe just a straight line, and so on. All of these are what we call continuous, and that is a concept we will explore later on in this chapter. But for now, let's talk about just the limit of a function being the function's intended height, the height it intends to reach. We can evaluate limits using a graph like we did on the previous page. We can do it using direct substitution like I showed you on the previous page as well. So you should always try this first. Okay, try direct substitution. So what that means is that in the case of this limit, the limit as x approaches negative 2 of x squared minus 2x plus 1 over x plus 3, which is a function that we will explore later on. This is called a rational function. We will explore rational functions in greater detail after we get through limits and derivatives. Okay? Curve sketching is an application of derivatives, so we will do that later on. But what I want to do to find the limit as x approaches negative 2 is simply plug in negative 2's everywhere I see an x. So this is going to equal negative 2 squared minus 2 times negative 2 plus 1 over negative 2 plus 3. And we can solve and get 4 plus 4 plus 1 over 1, which would equal 9. Okay? That means as x approaches negative 2, as I move to the left 2 units, this curve right here, x squared minus 2x plus 1 over x plus 3, would have a height of 9. All right? So direct substitution, all good. Next one, this would be a parabola. Okay, we have explored parabolas. You did them in great detail in grade 11. But all I want to do here is replace the x with a 3 in this case. And it's going to equal 16 minus 9, which would equal 7. That means as I move 3 units to the right, this curve would be up 7 units. Right? That curve would look something like this. So over 3 to the right, I'd be up 7. Those are examples of direct substitution. You should always attempt that first. I wouldn't expect to get a whole lot of questions like this on a test. I might put one in there to kind of keep you honest. But what we're really looking for here, the kind of the big point that we're going to take from this lesson, or this video, is something called an indeterminate limit. And that occurs when direct substitution leads to 0 over 0, or infinity over infinity. We'll explore that one more later on. Okay? But if I get 0 over 0, okay, these are the techniques that I'm going to use to kind of get rid of that indeterminate form. An indeterminate limit means that there's a factor in the numerator and the denominator that is the same. Okay, there's something happening, something weird about these functions. There's something happening in these functions that's causing you to get 0 over 0. Our goal is to eliminate that and then evaluate the limit. So I'm going to factor, I'm going to rationalize. So factoring, that's why we spend so much time factoring. All right, rationalizing, so when you get radicals, we can expand, or we can find common denominators. All right, this is when you have a complex fraction. This method works good. You could also use a trig identity when we're doing limits of trig functions, but that's for another video as well. So I'll show you what I mean by getting 0 over 0. If I fill a 4 in to the top, I get 4 squared 16 minus 16, that gives me 0. 4 on the bottom, 4 minus 4 gives me 0. So 0 over 0, that is an anomaly, a mathematical anomaly. You can't divide by 0, and 0 divided by 0, what does that even mean? Okay, so there must be something I can do to this, one of these 5 things, that will help me simplify or reorganize this limit so that I can actually calculate it, so I can figure out what the intended height of the function would be. And you might say to yourself, well, that top, I can factor that. And you can use the difference of squares. So in this example, I'm going to factor. So I would write the limit as x approaches 4. This is a common mistake too. A lot of people drop that limit notation right off the hop. Don't drop that until you actually go back to direct substitution. So how would you factor the numerator? X squared minus 16. Well, that's x minus 4 times x plus 4. That's a simple difference of squares. And now you might notice that I have an x minus 4 in the numerator and in the denominator, which would divide away. It would leave a 1 here and a 1 here. It's at this point that I can go back to direct substitution. So anywhere there's an x remaining, I would fill in a 4, and there's only an x right there. So this is going to equal, as I said, drop the limit notation. It would be 4 plus 4. You could write times 1 divided by 1 if you wanted, but that doesn't change anything. So this function actually intends to reach a height of 8 as x approaches 4. All right, here's another example. If I fill a 0 in for h, okay, 4 plus 0 is 4. The square root of 4 is 2. 2 minus 2 would give me 0 over 0. That is an indeterminate limit. Okay, direct substitution leads to 0 over 0. That's this situation. So what I'm going to do in this case is, well, I got to do one of these 4 things. I can't factor anything. There's nothing to expand. Okay, it's not a complex fraction. It's actually this method right here. I'm going to rationalize because there's radicals involved. And what I'm going to do to rationalize this is I got to multiply both the top and bottom by the conjugate of radical 4 plus h minus 2, which would be radical 4 plus h plus 2. If I do that to the numerator, I do it to the denominator. Now think about this. Really, I'm multiplying top and bottom by 4 plus h, or the radical 4 plus h plus 2 over radical 4 plus h plus 2. That's like multiplying by 1, right? So it's really, this is a legal mathematical move. So this is going to equal the limit as h approaches 0. Now there's a shortcut you can use, like this times this. Radical 4 plus h times radical 4 plus h would give me 4 plus h. If you did this times this, you'd get plus 2 radical 4 plus h. And then this times this, minus 2 radical 4 plus h. And those things would cancel one another out. Okay? So the shortcut here is actually, instead of going first times first, outside times outside, inside times inside, last times last, when you multiply something by its conjugate, you can just square the first term, square the second term, put a minus sign between them, or go radical 4 plus h times radical 4 plus h, negative 2 times positive 2. Look, follow that arrow. Negative 2 times positive 2 would give me a negative 4. Now on the bottom, I'm just going to leave this as 2 separate factors. So it's h times radical 4 plus h plus 2. And the reason I do that is because, remember, you are trying to get a factor to cancel from the numerator and the denominator, like I did over here. So 4 plus h minus 4, if I simplify that, that would leave an h. Okay? 4 minus 4, they go away. On the bottom, I have h times radical 4 plus h plus 2. Here's where I would get rid of the h's from the numerator and the denominator, and this is where I would be able to go back to direct substitution. So anywhere there is an h remaining, I am going to fill in a 0. Now just be careful. Okay, you can drop your limit notation. What would the numerator equal? The numerator would just be a 1. And on the bottom, this would be the square root. You don't have to show this work. 4 plus 0 plus 2. Well, that's the square root of 4, which is 2, plus 2 gives me 1/4. So as h approaches 0, that function approaches a height of 1/4. All right? Try these ones on your own, and I'll show you the workout. I'll do a couple more examples, or I'll finish these ones up in the next video.